Okay, we're going to do chapter 10. I think I'm just going to combine 10.1 and 10.2 into a single lecture. Because 10.1 is really short. Chapter 10 is on tests using what's called the chi-square distribution. It's spelled, if you spell it in English letters, it's C-H-I, but it's pronounced chi. It's a Greek symbol that is, it looks like an X, so it looks like that with like extra curly or something. But anyway, that's chi, and it's going to be squared, so we'll see that notation. You'll see it in a bit. But anyway, test using the chi-square distribution. There are two tests that we include in the book that use the chi-square distribution. We're only going to go over one of them. So we're going to do 10.1, which is introducing you to this distribution. 10.2, which is called goodness of fit test. 10.3 is a test of independence, but I can trim it down, so I'm going to trim that off, and we're just going to wrap it up at 10.2. I think I'll probably do 10.3 and put it up as an optional lecture. If anybody needs to like brush up before they transfer to a four-year school on statistics, I don't want to shortchange them, but it's not going to be in the final. You'll just have to do the 10.2 problem. Anyway, chapter 10, test using the chi-square distribution. 10.1 is introduction to the chi-square distribution. And I'm going to start using notation, which is going to look like that. And you'll see it actually on your calculator like that when we refer to chi-square CDF. Again, even though they call it the chi-square distribution, it is technically a family of distributions. A family of, and it is not symmetrical and it is not bell-shaped. Right skewed. It is right skewed. We will see. I'll sketch a picture in a bit. But so this will be a different picture. Right skewed distribution with a single parameter called degrees of freedom. It's conceptually the same as the degrees of freedom in the t-test. Degrees of freedom is a concept that comes up a lot as parameters to different distributions. Let me draw it. Okay. So one thing to note is when I draw it, I'm going to have that 0 there. This is going to be chi-squared values. And it does not go negative, so it's only going to be on the positive side. You can only take on positive chi-squared values, so that the random variable will be positive. It's because it's this actual square of something that we're not going to get into. It's got this big hump over here, and it trails off. Now, I also like to put some common values so you know what kind of values you're going to be dealing with. With the standard normal curve, it was like 1s, 2s, 3s. You never really saw 7s and 8s. Here, it can be, you can see like 5s, 10s, so you often will get like values that are in 20s. It goes to infinity, and you can get extremely large chi-square values. You will see one that's a value of 10,000 in the homework. But anyway, just be aware it goes to infinity, can't be negative, and you do get these values that are higher than what we've seen for test statistics. All right, not symmetric. And my notation, so I'm going to be like I put n for normal, t for t, and then I'm going to put chi-squared, and I'll put the degrees of freedom here. Let's say this is chi-squared 5. No. This is chi-squared 3. And if you care about how that degrees of freedom affects the shape, which I'm sure you do, if you do chi-squared with a higher number of degrees of freedom, it just gets flatter and like that. It's still right skewed, but it just kind of flattens out and stretches out further to the right. Doesn't matter, we're not going to be sketching it accurately. I'm going to do rough sketches to see p-values on this, but and every time I draw one, I'll just draw a hump that looks relatively like that. I'm not going to bother getting the shape super accurate, and I just draw pictures for visualization purposes. Okay. Can I fit it here? Yeah, I can fit it here. Find the following, let chi-square be a random variable that has these distributions, depending what degrees of freedom I provide. These problems are just going to be getting used to using your calculators to do the probabilities on this new distribution. Let chi-square be a random variable with a chi-square distribution. It's kind of redundant, but whatever. Find the following probabilities. I'll do one here and then I'll erase. Make sure I'm in screen still. Look at the glare. Where's the glare coming from? Hey! All right. Find the following probabilities. Okay. So we're going to go back to probability notation. Probability of some inequality involving, if it was z, I put a z there. We don't really use that for t, but it could be done. Use x for a generic random variable, but here it's going to be a chi-squared random variable. And I'll have, leave some space for some lower and upper bounds. 3.4 is less than chi-squared is less than 8.2. 4 df is equal to 7. Completely just made up numbers, just again to get us a feel for how we're going to do this. And how we're going to do this is, I'm going to draw a sketch that looks roughly like that. I don't need to label it super accurately. I'm going to put my notation here as a reminder so I don't have to go back to the problem and hunt for my degrees of freedom. It's right there, 7, but I'll put it right there for convenience sake. This is my chi-squared axis, so these chi-squared values of 3.4 and 8.2 are just going to be on this, which is a natural number line, and it does have 0 there. I won't be marking that in the future, but I'm going to emphasize it now. It's the whole distribution starts at 0, it does not go negative. This is a regular number line, so 3.4 I'm going to say is here-ish, and 8.2 is going to be here-ish. And I'm going to just shade so I can visualize my lower and upper bound. Oh my god, I didn't leave me any space. Just shift it over. I should have just erased. I'm going to do more anyway, but anyway, let me just try and make this a little bit more readable and leave some space on the right for me to actually show what you're going to be typing into your calculator. And so when you're trying to do a normal probability, you use normal CDF. When you're trying to do a probability for the t distribution, you use t-CDF. Guess what you use for chi-squared probabilities? That's right, chi-square CDF. Under the same column, under the same menu distribution. I'm not sure if you have to scroll. Let's see. You got to scroll a little bit. I can see chi-square PDF, which is not it. It is CDF. Let me emphasize that. You always have what's called a PDF and a CDF, and we are almost always using CDFs for areas under curves. We did do that. I did teach a shortcut of using binomial PDF, but that was because it was a discrete distribution. Normal CDF, t-CDF, and here chi-square CDF. Lower and as usual, lower, comma, upper, comma, any parameters that you need, and here it's just one parameter of df. Oh my god, I feel so bad that's messy. But anyway, chi-square CDF, I'm going to put my lower there. My lower bound is 3.4. My upper is 8.2. And then chi-squared has one parameter called the degrees of freedom, and is provided right here, and I put it right there for convenience. And so I'm just going to tack on 7 as your df. If you got a menu, it should walk you through all those inputs. But if you have the older versions, you got to remember, but it is pretty much like the others. Lower bound, upper bound, and then the parameters in a particular order, but if there's only one, thankfully, it's just that one parameter degrees of freedom at the end. 5304. Yeah, okay. It's a probability, so 4 places, but if you want to go with 3 places, it's fine, because we will be using this strictly for p-values in the next section. So 3 is enough to do a p-value comparison to your significance level. And for 10.1, that's all we're doing, is just getting some practice with this. Yeah, I just got 2 more. I'm not going to waste time, but I'm going to do the one side inequality. So B, probability that chi-squared is less than 6.64, and I can't just give you that. I would need to specify your degrees of freedom. 5. Okay. I'm going to draw my generic chi-squared. I'll put my notation there, and then I'll just visualize my region by marking off 6.6 somewhere and just making sure I'm shading in the correct direction. I'd say 6.6 is there. And then I'm just going to make sure I'm shading the correct side. Left or right, the chi-squares is what you're shading, the chi-squares, which are less than 6.6. You're doing this, I don't want to call it a left tail because it's not really a tail. The left side, we'll say. And we're ready to go. Oh, let me put what we're going to be typing in. I'm going to call the same function as before, chi-square CDF. Lower bound, it stops at 0. 6.6, and my degrees of freedom are 5. Now you're probably used to using negative infinity if it doesn't have a lower boundary. Hold on a second, and I'll just talk about that for a bit. Let me just get my answer here. Okay, so I got 0.747, and that 8 rounds up to 9. 7479. And so you technically have a left boundary of 0 because it does not go past 0, and an upper boundary of 6.6. You could use infinity. The idea is technically the number line goes past there, but the probability is just 0 there. So even if you include negative infinity as your lower bound, it will still give the same answer. I'm pretty sure I've done that before. Let me just do it again, just so to make sure I didn't make up something. Okay, so now I'm redoing it with negative infinity, and I get literally the same answer. So either way is good. I'll be sticking with 0. Well, I was going to say I'll be sticking with 0 when I do it. Full disclosure, we're never doing this again. You do a couple of these for 10.1, and then never again, because we're going to be using this to find p-values. And for our chi-squared test, and because it's a right skew distribution with only a right tail, your p-value is always going to be a region that is a tail probability, meaning only right tails. So you will only be getting p-values on right tails. So you'll never see a problem like this where we're going left after 10.1. All right, but I need my degrees of freedom. You're going to be doing things more like this, where your chi-squared is greater than that to kind of find a p-value. Here we're going to do df is equal to 3. And so when we get to the stage where we're doing tests involving the chi-square distribution, we'll get a chi-squared test statistic. Let's say we got 5.7, and it doesn't matter what kind of test. There is no left or right tail test. It's only one particular test, and the p-value will always be a right tail like this one. So we'll always be doing the right tail probabilities in the next section. Okay, oh, I gotta write out what I'm doing. Chi-square CDF. Lower bound 5.7. This time it does go to infinity, so you are using 10 to the 99, and you will always be going from your test statistic to 10 to the 99 and your degrees of freedom for a p-values. And that's a computation that would be the kind of thing you'll be doing to find p-values for your tests. One, 2, 7, 1, 5, and I gotta round that one up to 2. So 1, 2, 7, 2. Perfect. Okay, and that's it. That's it for 10.1. Just getting you a feel for it, and it's gonna make sure you can do regions with a lower and upper bound, a right side region, and a left side region, and a right tail region, and then we'll just be focusing on right tails in the future. Okay, but since I was so quick, I don't want to just have a separate video, or I'm just going to do 10.2 right away. It's also short. Well, I don't want to say it's short. It's not as long as some of the others. I'll probably have to do it slowly and make sure we know we're doing the steps because we're building tables. .2 is on chi-squared goodness of fit, hyphenated, goodness of fit test. Which means you're testing to see how good of a fit something is. I don't know what else to say other than that until we see an actual example. I will mention that you're going to start off with your null and alternative as any test. But instead of a parameter equaling and less than or greater than, it's more of a concept, and you can write it out as a phrase. The generic version of it is, the null is the distribution is as claimed or expected and the alternative is the distribution is not as claimed. My second example will be testing the fairness of a die. Don't really do this down because we're going to get to it. We're going to test the fairness of a die. And the idea is we're going to, let's say we roll a die 30 times, which is what we're going to do. 30 times, and you expect each outcome to be equally likely for a die roll, a fair die at least. And so if you're rolling it 30 times, you expect to get 5 1s, 5 2s, 5 3s, 5 4s, 5 5s, 5 6s. That's the expected distribution, is to have it evenly distributed. Uniform distribution was the technical term. And we're going to test a die, if the die is fair, to see if the actual outcomes kind of are close to this. You're never going to roll it 30 times and get exactly 5s for all of them. It'll be some variation that we expect, but you definitely should get something close to that. So in that case, my null will be the die is fair. And then the alternative, if you have evidence that somebody's cheating with the die, meaning it doesn't look like it's evenly distributed, we'll say the die is unfair. So we can rephrase that in different ways depending on the context. And you'll see in a bit, but anyway. So this is a generic form. You can phrase it sometimes in more colloquial language. The test statistic, the second step after null and alternative, is to do the test statistic. And ours is a chi-squared test statistic. And what we're going to have to do is sum, which is why we're going to be resorting to the list. What we're going to be doing is O minus E squared. That is a capital O, not a 0. Capital O minus capital E squared divided by E. And we'll get a value. That is a chi-squared that lands somewhere on that curve, like that 5.5 that we dealt with earlier. And then we'll get the p-value by doing a tail probability, always a right tail, off the distribution that this statistic has, which is chi-squared with k minus 1 degrees of freedom. So just like the t, do I still have it? Yeah. Anytime you're working to do some sort of a hypothesis test and you always have a test statistic to work with, you should always know the distribution, and here they'll specify it. Z, when we did that for proportions, was n01. The t that we did for means was t with n minus 1 degrees of freedom. And chi-squared here, this is our statistic we'll have to compute, and then once we do that, we're getting our p-value off of this distribution, which is what we just worked with in 10.1. Okay, so that's the thing that's going to appear on your formula sheet. I haven't really defined all these new symbols that we've never seen before. Chi-squared we know is a new distribution. O stands for observed. It is the observed frequency for each category, and there's going to be multiple categories. Capital E. Capital E has a formula that you may have to be computing. It's n times p. We'll elaborate on that in a bit, but So we'll have to compute E's on our own, but what they are defined to be is the expected frequencies of each category. Okay, and that's all you need. It does take a little building in the list feature to get there, but all it's involving is O's and E's for each category though. How many categories? That's important, and that's what K stands for. The lowercase k here is the number of categories. And we're ready to do an example. So let's see. I'm just going to copy this down. And then make room for an example that's going to involve a table. Okay, suppose the population of the United States is, and in reality, when they do the census, there's, I don't know, like a dozen categories for ethnicity that they'll let you choose from. You'll see a Berkeley list of the demographics of their student body, and it's got, I think, more than 12 rows. I don't know, but there's a lot of categories. For simplicity's sake, we're going to suppose the population of the U.S. is only composed of 4 groups. So apologies to anybody that I'm omitting. I'm not trying to be not inclusive, but I'm trying to just trim it down and streamline it is what I was trying to say. We're going to go with 15% Asian, 12% Latino, 30% Black, and 35% white. That's 100%. Again, just trying to streamline the categories down to 4 so we can just see how this test works. But anyway, that's our fake breakdown of the United States population. Okay. A sample of 78 students from a local college, a fictional local college. Report the following. So we're going to look at how these 78 students break down racially. In theory, if everything was, all harmonious, these 78 should break down into these percentages if you don't have any kind of social problems or racism or institutionalized racism holding people back, causing disproportionate representation. So let's see. And this is, again, made up data. Let's say there's 7 Asians, 23 Latinos, 18 Black, and 30 white students in the 78. If I didn't give you that 78, and sometimes I don't, sometimes you just get the table. You will need that total. So you would add 7 plus 23 plus 18 and 30 to get 78. So you wouldn't need that total if I didn't give it to you here. And I was just checking my total. Okay. Perform a goodness of fit test to determine if represented proportionally. Okay, and we're going to go through the steps. I didn't give you a significance level. We will need a significance level. I'll put it at the end. I can put it now. Sometimes because I'm going to give you two different ones. So when we get to our conclusion step, we'll have two parts to it where we'll look at is there enough evidence at the 5% level, and then after if there's enough evidence at the 10% significance level. But let's go through steps here. I'm going to use Roman numerals, reflecting the same Roman numerals that I did before for the 4 steps, but in the homework it might be A, B, C, D, or just completely different numbers. Stating null and not alternating, alternative hypotheses. Okay, HOHA. You can write them any way you want, but I usually just stack them on top of each other. If it was proportions, it would be P. If it was means, it would be mu. And if it's a chi-squared goodness of fit test, it is a phrase that you have to capture the idea of the distribution is as expected, the distribution is not as expected. And in the context of what we're trying to test for, you can say the races, they're ethnicities, not races, and I do know the distinction, but let's go with this. Races represented proportionally is going to be our null. We assume everything's good and everybody gets proportional representation as they should and everybody's living harmoniously, and your alternative is that the races are not represented proportionally. So that's an interpretation of that generic, the distribution is as claimed and the distribution is not as claimed. I'm going to abbreviate there. Okay. That's how we're breaking it down. We assume they're represented proportionally until we have evidence otherwise in the form of a small p-value that is below the significance level. Next step. Calculate the test statistic. And often when I ask that, I don't even really specify which test statistic you're computing. You're expected to know that based on the test you're doing. This one is the chi-squared one. And so we need to build up towards, I erased it. Why did I erase it? Okay, in addition to the z and the t, you now have a chi-squared. I'm going to make some room for it. I'm leaving my errors because I'm going to ask about errors later. Okay, that's what we're doing. We need O's, we need E's, we need to sum it for all the categories. So we're going to go to the list feature. And I'm going to put my O's. Oops, let me leave some room. I'm going to put my O's, my E's. This is what I'm going to be putting into the list feature. O's in L1s, E's in L2. But on the side here, on my board work, I'm going to write the categories down, the groups down. Asians, Latinos, black and white. You're obviously not going to put that in the list feature, but that's going to help me, keep them straight as I work through building my list. Okay, my O's. Erase the definitions, but the O's stand for observed. The observed frequencies in your sample. The 78 people, 7, 23, 18, 30. Wait, what did you say? 7? 7. 7. I feel like I said 17. 7, 23, 18, and 30. Okay, suppose we did not have that 78. You would need a total. You're going to need the total, not for your formula, but because we're going to use it for the E's. So I would add that up. You can put in L1 and just sum L1, or you can manually add them up by typing it onto the main screen. Either way, 7 plus 23 plus 18 plus 30 is equal to 78. And that's the observed frequencies, the actual breakdown of our sample. E's are expected. I'm going to put this. Okay, I'm going to write some notes here, make a note of it, then I got to erase it because I got to make some room to build the rest of the table to get to what we need to. But the E's require a computation. The computation I mentioned was n times p. Now n is the number of points in your sample, which will be 78. We're going to write that in. N is 78. P is proportions or probabilities or percentages, however you want to think of it. It's the percentage or the proportion of that category. What did I just write? Proportion, probability, percentage, any one of those could be thought of as this P. Okay, but anyway, I'm going to erase it right away. Anybody, I wrote that down earlier, n times p. And I'm going to do it right here. I'm going to start to do it for these categories. So for Asians, the expected number of Asians out of 78, what do we expect? We expect a certain percentage of the 78 to be Asian. What percentage? These are our proportions based on the population proportion. So we want basically 15% of, we expect 15% of the 78 to be Asian. And that's a computation. N times P, the percentage that should be in that category. 78 times 0.15. Okay, I got 11.7. You can't have 0.7 on Asian, but despite that, you leave it with the decimal for more accuracy in doing this test. So even though it's not a possible number of Asians, you don't round to whole numbers. You can work with decimals for the computation purposes to getting a p-value. So leave the decimals. One decimal place is fine. All right, and I'm going to start. I'll do the next one. I'll write out the steps to the next one, and then from there I'm just going to do it. Next one, I want to figure out the expected numbers of Latinos. I'm going to be doing n times p again. N is still 78, but I'm expecting, if everything were good racially, I'm expecting what percent of the 78 to be Latino? We expect 20% to be Latino. So I want to do 20% of 78, and you get that by multiplying 78 times the decimal form of that percentage. So 20% of 78 is 15.6. You expect 15.6 Latinos. Notice you don't expect them to be equally represented because they're not equally represented in the population. You expect proportional representation. That was mentioned in chapter 1, and this is proportional representation. Getting about 12 Asians and maybe 16 Latinos is fairly accurate proportional representation. All right. I'm going to do the remaining categories real quick. It's unrelated to this, by the way, so you can completely ignore that. This is purely based on the 78, breaking down that 78 students by those percentages. Okay, so I expect 30% of my 78 to be black. 78 times 0.3, 0. 23.4. And I expect 35% of my 78 to be white. 78 times 0.35, and I got 27.3. Okay, I gotta make room for a couple more columns, 2 more columns to be exact. But anyway, that's how you're doing it. The n, the total in your sample size, times the percentage or proportion or in decimal form. And what that does is gets a breakdown of the 78 and what we expect it to be based on those proportions. Okay, so recapping real quick. If our null is true and the races are represented proportionally, then that 78 should break down into 15% of the 78 should be Asian, 20% of the 78 should be Latino, 30% of the 78 should be black, and 35% of the 78 should be white. And that's what that computation was right there. Meaning that if you total that up, you don't have to, but if you did, it should total to 78. Now if you do any rounding, which I don't think we did, because I had nice round percents, but it might be a little bit off. It might be 77.9 or 78.1. It might be a little bit off from that, but it should be very close. And if you didn't do any rounding, it should add up to exactly 78. The idea is you're breaking down that 78 into what we expect based on the percentages, and then you look at how it actually broke down when you survey these people, and you can see who's underrepresented and who's overrepresented. Asians are a little bit underrepresented. We expected 12-ish, 11.7, only 7, so they're slightly underrepresented. Latinos are overrepresented. We expected 16-ish, there were 23. Blacks were underrepresented. We expected 23, there's only 18. Whites were overrepresented, 27 we expected, there was 30. Is this far enough off? You're not going to get exactly these amounts, obviously, you can't have decimals, but you're not going to get 12, 16, 23, and 27 exactly. You expect some variation, you expect things to be a little off, but if they're way off, I mean, obviously if you had, 70 white people, and 2 and 1, and what I got, 4, obviously this is not a good school to go. This local colleges discriminate heavily, and you're definitely going to get a small p-value, which is strong evidence that you can sue that college for discriminating. It's not that bad. Is it bad at all? It doesn't look that bad. 7, and I'm not trying to be dismissive of anybody's concerns, but those seem pretty close. But we have to analyze it not through my feel, but based on a p-value. So we're building towards that. And I'm going to build it in 2 steps. Let me look at the formula. You can either do it in 1. This is purely optional in how you're getting to that expression. I want to sum that expression. I need to build towards that expression. And the way I'm going to be doing it is 2 steps. I'm going to do that O minus E squared. I don't want to do too much, but I will do 2 steps in 1. I'll subtract O minus E and square at the same time. 2 steps in 1. But then I'll hold off on the 3rd step for my another column. Then I'll take each of those, and I'll divide by E to get literally that expression there. And then what do I want to give my chi-squared random variable? Sigma. That's what summation. So I want to sum this, and that right there will be my chi-squared statistic, my test statistic, which I'm then going to use to get a p-value. All right, let's do this. No, I don't know if you need that, but I'm going to make room for my formulas. I'm going to write in red like I usually do. Anyway, go ahead and put your O's in L1 if you haven't already. E's, we pretty much, I mean, you can do it in the list, but I would say just do it manually on the main screen and then just fill in this table on your paper and then type it in from there. But either way, these are just going to be entered into L1 and L2. 7, 23, 18, 30. Okay, so I got it in. I'm going to build towards this first as a baby step towards my ultimate expression. So right here, L3. Make sure in the column header as usual. We haven't done this in a while, but you need to be in the column header on your calculator. So I'll go over to L3 and make sure you're up in the column header with L3 highlighted. And then let's see what we need. The parentheses are important. I got to subtract first, then square. So I need to tell it to do that in that order by using parentheses. My O's I want, which I want to grab from L1, minus my E's, which I just put in L2, so I'll subtract L2. And I want to do squaring at the same time, so I'll raise it to the 2nd power. So L3 is equal to parentheses, L1 minus L2, close parentheses, squared. We got 22.09, 54.76, 29.16, and 7.29. Next step, I want to use that column. I didn't want to do too much at once, but now I need to just take that and divide by E. So in L4, I want to take those, that's minus squared thing that I just put in L3, and I want to divide it by E. So I'm going to just divide that by L2. So L4 is going to equal L3 divided by L2. Make sure in the column header as usual, L3 divided by L2. And I got 1.888, 3.5103, 1.2462, and 0.26703. And just looking at the formula, that's your expression. They want you to sum it for all the categories. And so we're going to quit back to the main screen, second quit. Find sum, which is under list, the same button as stat, second list, over to math, down to sum. I want to sum this column right here, L4. And I got 6.911, a lot of decimals, and I round it off wherever I feel like it. I'll do 3 places, but for no particular reason. 2 or 3 is fine for a chi-squared variable. Okay, and if you round things differently than I did, you get a slightly different answer, but you should be fine, so don't worry about that. That was step 2. I erased the header, but that was 2. Calculate the test statistic. We are going to go to step 3, which I need room for. I'm good with this. I got all the information that I need over there. So 2 was test statistic. 3, calculate the p-value of that test statistic. Okay, 6.911 is my chi-squared test statistic. How am I going to get my p-value? I need to know its distribution. That's my statistic. That's the distribution right there. It's a chi-squared distribution. Let me draw it. Hump, tail, that's my drawing. My notation, so I know what parameter I'm going to use. I need to specify that. It wasn't just given. We have to know that it's k minus 1. K being, if you recall, I wrote it on the board, but I erased it, number of categories. How many categories do we have in my simplified world view? 1, 2, 3, 4 categories of people. So I want to do 4 minus 1, 3. Let me, just in case you're only half paying attention and are going to tune in later when I'm almost done, that's from k minus 1, k equals 4 categories. Okay. Anyway, based on that distribution, I can get a p-value by using my result there, 6.911. I'm going to put it right about there. And your p-value is always, doesn't have a left tail. Your p-value is always a right tail for your chi-squared tests, both the one we're doing now in 10.2 and the one we're not going to do in 10.3. It's always right tail. Okay, so let's do this. Same thing we did in the 10.1. Chi-square CDF is the function I'm going to be calling. My lower bound is 6.911, or some sort of rounded version of that. You can round it differently and it should be fine. My upper bound is 10 to the 99, always a right tail, always going to positive infinity. And then my parameter is at 3, the degrees of freedom, which I got by doing k minus 1 again. Okay, that'll give me a probability, or that area in that right tail, and that is my p-value. That's a probability that we would get this result, or sorry, this breakdown by random chance. So is there racism at work for the disproportionate representation, or is it just randomness? And we'll see once we get a p-value. Can't really tell just by glancing at it. Like I said, I thought it wasn't that bad. Maybe my judgment is skewed. 6.911, 10 to 99, 3 degrees of freedom. 0.07478. I'll round it to 0.075. Okay, that's my p-value. I can't make a conclusion yet unless I know the significance level, which I have not given you yet. Let me break this down a little bit. Spend a little time talking about it. So, if not by sheer coincidence, but if your breakdown, these are what expected again, and if you actually had observed roughly 12 Asians, 16 Latinos, 23 blacks, and 27 whites, if these were in line with what you expect, you get a chi-square that's near 0. This is good. Everything's working out exactly as expected. And if you get things that are slightly off, it's going to be here. If you get things that are further off, it's going to be here. And if you have severely disproportionate representation of these groups, it'll be way out here. And you're going to do one for homework. That's the actual breakdown of Berkeley students with all 12 or so categories. They break it down very finely and are very inclusive. It's Berkeley, you know how they go. And you're going to do a test like this. And spoiler alert, you're going to get a super high chi-squared value, which is strong evidence that representation is not good at Berkeley. I don't know if you guys knew that, but it's not. Okay, let's finish this up and draw our conclusions. Are we going to sue this school? I got to give you 2. So there's going to be 2. Therefore, is your conclusion? But I'm going to actually ask 2 separate conclusions. Is there sufficient evidence at the 5% level to conclude the races are not repped proportionally? I'm going to abbreviate. No, I shouldn't. So again, did I erase my null and alternative? We assume they are represented proportionally unless we have strong evidence in the form of a low p-value otherwise. So do we have sufficient evidence to reject the null and sue the school for discrimination? That's essentially what it is, even though we're not really going to sue. I'm going to erase this. We are good with that. The only thing that is useful for is getting a p-value, but the p-value tells us a lot. It tells us what we're going to do. Sue them or not sue them. And it depends what standard we're using. Let me rewrite this. I'm sorry if I'm going to take a little bit of time, but I need space to make some comments. Is there sufficient evidence at the following significance levels to conclude the races are not represented proportionally? We need significant evidence to go with that they are not represented proportionally. We give people the benefit of the doubt unless there's strong evidence that something is wrong. Let me see. Is there sufficient evidence at the following significance level to conclude that races are not represented proportionally? Yes. Okay. 5%. And then we'll do 10%. Different standards. Higher standard, a looser standard. If you're using this, that means you're really eager to sue people. This one, you're more hesitant to sue them and require more evidence to make that jump. Okay, our p-value is relevant. P-value 0.075, 7.5%. There's a 7.5% that we got that breakdown of students by random chance. That is not meeting that high standard, that higher standard. That's not enough. So no. Insufficient evidence. Do not reject. We are going to let that school continue to operate and not say anything about it. We're giving them the benefit of the doubt. So we think that breakdown was a little bit off by randomness, not because of racism. P-val. Still the same p-value, but now it's a looser standard. This is a standard for somebody who's eager to sue. And now you are below that standard. You have a small enough p-value that you're going to sue. Yes. Sue them. You're rejecting the null, that the races are represented proportionally, and you are going with the races are not represented proportionally. Now in reality, you know, there's social issues and all kinds of things that would complicate this conclusion. But the general idea is we do not think they're represented proportionally because the p-value is small enough where we're willing to reject the null. All right, we're going to do one more regarding dice, but it's the same idea, it's the same process. There's no left or right tail you have to worry about. It's always right tail with the chi-squared. We're going to do one more because I do want to make sure we can do that. Expecteds, knowing how to do the expecteds is the thing that trips people up. We'll come back to that once I pause and eat my dinner. Okay, so a common thing is what we did ethnicities. You can do flavors of M&Ms in a bag and see if the proportions are as they claim. You can also test the fairness of a die with this test, and that's one of the common things. And I had a lab that was based on you literally rolling a die and seeing, but here we'll just do a made-up one. Okay, so suppose a die was rolled repeatedly and the following results are recorded. These are results: rolling a 1, rolling a 2, 3, 4, 5, or 6 are your possible outcomes. They're not doing probabilities, they did frequencies, so this is a frequency table from chapter 2. 18 ones, 34 twos, 25, 41, 28, 19. It's hard to tell by glancing at it if that's off. It does seem, they should be roughly the same. They're equal probabilities, equally likely, so you expect it to be the same all the way across, and they're not. They're, you expect it to be roughly the same all the way across, not exactly. And it's hard to tell if it's really far off from that. Anyway, we're going to perform a hypothesis test at the highest standard that we do, 1%, to determine the fairness of the die. Okay, and I'm going to do the follow-up questions with the errors at the end, but for now, let's go through our null alternative. The whole process is 4 steps. The null for the chi-squared goodness of fit test is the distribution is as expected or as claimed. We can summarize that by saying the die is fair. We default to assuming that the die is fair unless we have evidence otherwise, and that evidence will be in the form of rejecting the null and going with the alternative hypothesis, which is that it's not fair. Okay, and then we need to do our statistic, which requires us to do a table. I'm going to go over there to do the table because I need some room. You need some O's, you need some E's. I'm going to go ahead and do it in one step. I think you've done enough tables where you can maybe handle multiple operations in one formula for L3, but if not, do it in the 2 steps that we did in our first example. Okay, the observed frequencies are right here: 18, 34, 25, 41, 28, and 19. The expecteds are, we're going to have to compute that, but the results, 1, 2, 3, 4, 5, where are they going to go? They don't. They're not things you're going to be entering. They're not data. They're like flavors or categories of things. They're like Asians, Latinos. So they're not actually numerical data that we're going to be inputting and doing computations with. They're categories. And just like the last time where I wrote out the categories on the side just so I can kind of organize my rows, I can put them there, but they are not going into the list. What I do need to put into L2 is the expecteds, and I got to figure that out. The last time I did it was for me to do the total number of data points, or the sample size, and multiply it by the percentage, or the probability, or the proportion. So it was 78 students and 0.15 Asians, 15% were Asians, so I did 78 times 0.15. And all that information was given in the problem. Now here we have a lack of that information, but you have to kind of figure it out. First of all, n is your sample size. How many data points do we have? They did not give us a total, so we need to know this total first. This is n right here, the total number of observations, the total number of rows of the die. I'm going to just put it into L1 and sum it since I'm going to need it in L1 anyway, and I don't have it ready, so no, I'm going to do it right now. 18, 34, 25, 41, 28, and 19. So I can quit, and I'm going to sum. Sum it under list, second list, over to the math menu, number 5 to sum, and I want to sum L1. And I get 165. That's my n. And then I got to break up that 165 based on the percentage that I expect to be 1s, 2s, 3s, 4s, 5s, or 6s. Again, they did not give us percentages, but our assumption it's a fair die. So now we're going to go back to chapter 5. It's not that bad, don't worry. We're just doing the probability for a fair die. We're assuming it's fair until the end, and we draw a conclusion. But for now, we're assuming it's fair. And if it's a fair die, what's the probability that you roll a 1? It's probably that you roll a 2. It's probably that you roll a 3, and so on. They're all 1/6. If you did a probability distribution, which we don't have to do, then probably rolling a 1 is 1/6, 2 is 1/6, 3 is 1/6, and so on. You can use a decimal form of 1/6 if you want. It's 0.1667 if you go to 4 places. That's rounded, and if you do that, things are going to be a little bit off because of the rounding. So if I do, and what so I need to use, the only thing I'm using here is a probability. Either one of those. Going back to my E. My expected number of 1s is, out of the 165, 1/6 of them I expect to be 1s. Can I do that? That's just 165 divided by 6, and I get 27.5. If you choose to do 165 in a decimal form, you did 1 divided by 6 and rounded it. You'd be doing that instead. It's equivalent, except it's rounded. I just want to see how far off it is. And you'll get 27.5055. I guess if you chop off that or round it off, you'll get the same. So it doesn't matter. It might cause things to be slightly off, but I don't care. Just as long as you know that they're all 1/6 probability, and therefore you're expecting the same amounts of each. 1/6 of 165, 1/6 of 165, 1/6 of 165, 1/6 of 165, and that's equal to 27.5. So we're expecting even numbers of all of them, specifically 27.5 of each, which totals to 165. So again, you're breaking down that 165 into what you expect, and you expect them to be evenly distributed based on it being a fair die. And note that phrase, evenly distributed, because if it's not a fair die or a gambling sort of problem, if it's like flavors of Lifesaver, let's say, which is an example on the practice exams, and it says they are evenly distributed, same idea. Evenly distributed means the same proportions of each. You'd have to count. This was 6 categories, so each one had a likelihood of 1/6. What did I just say? Evenly distributed. Means you're breaking up in an even way. So you got to figure that out a little bit, but be aware that evenly distributed is essentially telling you the probabilities that you need to use, or it's giving you enough information to figure it out. Again, text me if you're stuck on any of them. But evenly distributed die rolls. All right, and let me enter that. And again, I'm going to just jump straight to that last column. I'm going to skip the baby step to get there. Okay, 27.5, 27.5, all the way down. And based on that, let me look at the formula. I'm going to have my O's, my observed in L1, expected in L2 that I have to compute and figure out. And in my L3, I want to redo this computation. I'm going to do parentheses. O's are in L1. Minus E's in L2, close it off, square it, and at the same time, again, I'm combining all the steps, but you don't have to. Divide by the E's, which are in L2. So that's what I'm going to type in. I'll write it big for you. I'm doing L1 minus L2. That's my O minus E, squaring it, dividing by L2. O minus E squared, divided by E. Okay, I got a bunch of values. Let me see, the light's not good here. 3.2818. Oh wait, I have it over here. That's fine. 1.5364. 0.22727. Why am I writing all this? I don't need it. So I'm going to dot like I did on the board when I was not wanting to spend time just writing down numbers that we're not even going to use. Verify those first three. This rest should be good, hopefully. And we should get the same chi-squared. If you got something different, maybe you made a typo along the way, but I'm not going to copy it all down. I want that sum. In this case, it's L3, unlike last time. I built my table differently than last time. Second list, over to math, sum L3. 14.309. 14.3 is fine. That's your chi-squared statistic. Now, we want to do the p-value. It's chi-squared. How do I know that? It says it over right there, chi-squared. K minus 1 is my degrees of freedom. How many categories we got? 1, 2, 3, 4, 5, 6. 6 categories. K minus 1 is 5. And that's my distribution that I'm using to get my p-value. 14.3 is there. Can't really tell how high that is until I really work it out with the calculator. That's just a generic form of it. It's not an accurate representation of that probability. Second distribution. Oh, let me write out what I'm doing. Chi-square CDF. 14.3 is my lower, 10 to the 99 is my upper, and my parameter is my degrees of freedom 5. That's my p-value right there. I got 0.0138. I'll go to 0.014. That's 1.4%. So these numbers are kind of off, these rolls. If it is a fair die, the probability of getting something that out of whack, and it is kind of out of whack, they're probably getting those die rolls that out of whack from what they should be by random chance is a 1.4% chance. That's like me getting 5 aces. It is not likely that it's due to random chance. It's more likely that they're cheating you and this is not a fair die. That's our conclusion. Well, is that our conclusion? Hold on. No. I gotta finish this up. What am I doing? Sorry, null alternative hypothesis. My test statistic via the table. My p-value right there. I'm going this way, sorry. And my conclusion. And I was mentally thinking we were comparing to the standard 5%, in which case we would reject at the 5% level. That's why I was talking about it being unusual and us thinking they're cheating. But this is the highest standard of evidence. 1%. We need to be less than that for us to conclude they're cheating and report them to the Gaming Commission. But that is not. It's a low probability, but it's not low enough for us to file a lawsuit according to this 1% standard. No, we're giving them the benefit of the doubt. As reluctant as I am to do that, according to our standard, we are not rejecting them now. We are essentially accepting the fact that, or the belief that this die is fair. Okay, so that was a 1% standard, and we did not meet that standard for us to reject. Okay, I got some follow-up questions. I want to do some errors. I didn't do any errors related to this. Let me erase all of this because I don't need it. I don't need any of this. I want to see my null and alternative, and I want to see my decision. To do any errors, to see what kind of errors were made in these hypotheticals. Suppose die is fair. Okay. And I usually do these in pairs, but in theory I can just give you one of them. It's just a single question about what type of error occurred. If this hypothetical scenario is true, the die was fair. But I also like to do the other possible scenario. If the die is unfair, what type of error occurred. This one's a lot simpler because mostly because our null and alternative are very nice, concise statements. Die is fair. The top one. Suppose the die is fair. Suppose HO is true. So that's saying if HO is true, what type of error do we make? Suppose the die is unfair. They're saying the alternative is true, which means, and we're not referring to the alternative, that means HO is false. The die is unfair. That statement for HO is false. Okay, so these are the hypotheticals described, or these are the the truth value of the HO, the null hypothesis, in this scenario and this scenario. What type of error occurred? We look at what decision we made. We chose not to report them to the cops, meaning we did not reject for both of these. They're different hypotheticals, but our decision is the same for both. Okay, which one was a wrong decision? Us not rejecting is like accepting HO. It was true, we kind of accepted it. That's the correct decision. Here it was false, and we kind of accepted it. We accepted a false statement. That was a wrong decision. Type of error? False, do not. Type 2. And we're done with everything. That's it. Like I said, I got to figure out what I'm going to do with the exam 3 and the final, because I don't really want to make you take both. Or at the very least, I'm going to make the final not cumulative, or sort of cumulative. I'll keep it short. There's a couple things I probably want to hit on the final. Make sure you go through them one more time. It's a take home so you can go through your notes. I won't make it as extensive as my usual final, but I'm definitely going to hit some things. So we'll see. I'll let you know.